Welcome to Global Math Department, everybody. My name is Jessica Bogie, and I'm your host this evening. Tonight, we are going to hear from Mike Larson and Ashley Goetz all about coding and geometry. We're excited to see new and familiar faces. So at this time, would everyone please take some time to introduce yourself in the chat window, tell us what you teach, where you teach, and if you have a Twitter handle, please make sure you share it. We love to make new connections at Global Math Department.
Yeah, thank you guys so much for joining us tonight for Breathing Life into Geometry with Coding. We have our 3 Twitter handles here on the right. CS and Math is our site about the intersection of computer science and math. This is Ashley's Twitter handle, and my Twitter handle is Bounds About Math. So we're going to start tonight with a 5 to 10 minute intro as people kind of get on and settled. It's going to be more like a storyline, and then we're going to, after that little intro, we're going to dip into the coding. I'm going to start into that.
Wait, hold on a second. You jumped a little bit. It's all right. Hi, everybody. Oh, I see Canada, Kentucky. Awesome. Lake Forest Academy. Hi, Joe. Texas. Anyone from cold Florida? It's about the same temperature as it is here in Illinois. Thank you, everybody, for joining us. All right, so before I turn it over to our speakers, let me explain just a little bit how our Global Math Department meetings work in case it's something new for you. The meetings are recorded and are typically available 24 hours after our meeting ends. So to view the recording, all you would have to do is come back to the same URL. This works really well to share the recording with anyone who may have missed it by sending them the link. Or if you wanted to share it with your math department or a teacher you know would just love it, then you can just email it and put that link right in the email. The global math community prides itself on being friendly and supportive, so we do have the chat room available for topical and general conversation throughout the meeting. The presenters and I will take time to catch your questions as they're going and try and answer them as they're going, so don't worry that it won't be noticed in the chatter. So our 2 speakers tonight are Matt Larson and Ashley Goetz, and it is all yours.
Yeah, sorry about that. I guess I really did jump the gun. I got excited. So yeah, we're excited to share with you the coding side of it. We just have a little introduction that's kind of a storyline. We usually like to start most stuff with the introduction. One guy that's changed our math pathways is definitely Dan Meyer, and this was from a 2013 perplexity session that I attended that he led. And I've held on to this quote. We make enormous promises to our students that the mathematics models the world that they live in, and that math has power. We attempt to make good on that promise with word problems that look nothing like the world and nothing like modeling as is practiced by mathematicians. So that's one thing we tried to live by for forever, and this was before we got into the coding side of it. And then we started to look a lot at our school about at the high school level about what jobs are there out there for math, and just so kids are aware. And we started to say, do you really think these jobs, how much math do these jobs have? So I don't know if you've talked to your students about this type of thing, or if you have maybe posters like this in your school, but like kids found it funny. I don't know if you can see what I'm circling here. There was like a welder on there, a taxi driver, some other things. And so we started to try to separate, like, okay, well, who uses more like middle school level math, and then draw a line, and who's using algebra and geometry. And what's interesting is that we really started to see a hard line where there was a lot of algebra and geometry in a lot of our digital and computing jobs. And then we started talking about, well, not all of them actually require math degrees, so maybe we need to be careful about saying practiced by just mathematicians, since, only, I think when you Google it, like there's 3,500 mathematicians maybe in the United States that are titled by that name. So, describing to kids, what does it mean to be not only college but career ready? So if you look at some of these like top ones, if you can read those, app developer, computer programmer, computer animator. You see a lot of things that do really bring in this coding that we're going to talk about, or programming in general, and not all of them require just a math degree per se. We wanted to share this little thread that we found on Twitter here, actually just a few days ago. This is a software developer talking to her friends, and there was hundreds of responses. Maybe you saw it, about their math and coding journey. Let me just share with you like 4 or 5 of these. Ed said he does web development for a living. Said he really doesn't do much past what his 7th grader's doing, equations, basic algebra, simple geometry formulas. A solid grasp of logic is important, but again, he iterates the addition, subtraction, multiplication, division, some more like you'd consider to be foundational middle school type math. Miss Kelly was talking about she has a dual degree, both in mathematics, applied mathematics, and computer science, and she hasn't gone much past advanced math in her user interface engineering. Some people were talking about how they hated math. They were not math people, which I hear from a lot of students. I don't know if you guys can resonate with that, but trying to get them to change their mind that they are, and just dipping their feet in a few different areas of math can. And a lot of these students that say they hate math, they actually find out that they like it a lot. Alan says down here, you can kind of skim that, but this kind of piece at the bottom where he says, the more you know, the cooler stuff you can do, which we've heard a lot as I've heard people present on NCTM. You don't necessarily need some of the higher math, but it really does allow for what you could call flourishing, is the way Francis Sue put it. So I was definitely reminded of his presentation, if you caught that from NCTM, about how things aren't necessary, but also to flourish, maybe opening your eyes to a new world. And to end it off, like Florian is a programmer. He says, I wish programming would have been part of math education. Like many here, knowing how to write code made it easier to understand some of the basic concepts. And that's what we found as well. So it's like a marriage. We're actually full-time math teachers, so we're definitely not trying to get rid of the math side, just really look at the intersection and how they complement each other. And so hopefully we can share some of that with you today. To kind of close it off, one thing I've been talking to about the way I've kind of phrased this to administrators is, what are we putting up on the pedestal, and is it balanced? So if you see the left side of the pedestal here, you have your classic tests. A lot of people do Map for Growth, or maybe just your state standard tests. It could be ours for Minnesota's MCA, or the AP College Board tests. Those are good. Those are easy to rank people on. But over here on the other side of the spectrum, you see, I don't know if you're familiar with the work by Seymour Papert, his work with computer language back in the 60s and 70s called Logo, and he had this actual physical thing he called a turtle. And so a lot of the programming we're going to do came from this project and how kids were experiencing math through programming. And we think it's great, and we're hoping to share it with you in a kind of a newer platform. But when you're talking about it with your administrators, you can say, is it balanced? Because we can't just have everything test score focus. What are we putting up on the pedestal? Let me share 3 things, 3 little, this is my 12th year teaching, and back in my 4th year, I had a lot of letters like this from students saying, hey, thanks for all your help and for staying after school and for helping increase my test scores. You did a great job. And I used to love those messages. And around 2015, I kind of is where I started programming heavily, and I did some Fab Lab training. And they started to shift. The messages I got started to shift a lot. And they said stuff like, if you read here, it says, looking at math from a different perspective, such as coding. Thank you so much for a wonderful year. That was about 2016 when we started to fully integrate coding in the geometry classes. And the last one here is a student who talks about the experience. And then if I just point out, I hope you will keep spreading coding and math. And so in 2018, we took that to heart for sure, and we started to bring it online, and that's how we're trying to share it. And so it's kind of just rests on a website called csmath.org. Everything's completely free. The lessons are there. There's a teacher guide and a student guide, and I'll let Ashley take it from there.
Yeah, thanks, Mike. Thank you all for being with us tonight. As Mike stated, we are full-time math teachers who have just recently in the past few years started integrating code. So here's our website, csandmath.org, if you want to pull this open in a separate tab. But really, as we kind of jump into our practice tonight, I want to just talk about kind of our 3 main goals as we present to you today. So first is we believe coding and CS can be a vehicle to target certain math skills. So that's going to be kind of what we talked to you tonight, being a geometry focus. We're still targeting certain learning targets or priority standards, whatever your district may for that piece. Our goal is to use code to improve some of these skills or practice these skills. Second thing is we're not looking to replace traditional math. There's definitely still a place, but we're looking to just infuse some of these career-ready applications into our curriculum. And finally, Mike and I have found this to work best if you've, I really like to kind of compare some of this to Fawn Wynn's problem solving. So just throwing in typically 1 per unit, 1 every other unit coding project where students are diving a little bit deeper into some of our math. So what we're going to start with today, Mike, would you advance a couple slides here to our first lesson? Perfect. All right, so the first lesson we get questions a lot from people at presentations and so forth about where do you start, especially if your students have no background to coding, and even if they do, how do we continue to challenge some of those students that maybe do have a little bit of a background? So Dan Anderson here is a high school math teacher in New York, and we want to credit our first lesson to Dan. Mike got to attend his session at NCTM back a couple years ago, and he just recently received the Presidential Award in 2018 here. So we want to credit this one to Dan, but you'll see a couple links here for you. What we find to make our time most useful together, rather than jumping in and having you code tonight, if you wanted to follow back on this video, working through this progression would be really good for understanding of the lesson. But we have a few links here for you.
So just to pause, actually, the bottom link here, the bit.ly link, that is a shortened URL for, we did a video, a vlog, I guess you'd call it, back in like 2018, I think it was, on this particular lesson. So if you were able to pull up that link, then you would get a video that goes back over it again if you needed it. So.
And we're going to throw in a lot of these links here at the end for us tonight too, so you'll have access to these slides. So we're going to walk through this as you are students in my classroom, of course, at a little bit of a quicker pace here. But please just pause us in the chat window if you have questions as we're going through. But you guys are going to kind of act as our students here for a second. So as we introduce this to students, we typically are working in Scratch. We've done a little bit in Python. You're going to see some Beetleblocks tonight, but we find Scratch allows us, with the lessons that we're doing, as we said, our focus is math focus, so we don't want to get bogged down by syntax errors and so forth. It's going to be more about the mathematical ideas through code. So as we start in Scratch, if you're not familiar with Scratch, it is a block-based platform. You'll see on the left-hand side here, these are all of our blocks, color-coded, which is really nice as you're talking through these pieces with kids. And on the right-hand side, we've got anything that you're going to code is going to happen on the right-hand side of the screen. So we've got our little Scratchy Cat here. Scratchy Cat is the famous, we call him a sprite in this program. As we move forward, the first thing that students will need to take care of as we start this program is they need to activate their pen tool. So Scratch has coined now a 2.0 version of itself. So we find this pen tool down in the bottom left-hand side in these extensions. And we'll just click pen, and that will open us up to a few more options here, a few more blocks to use. So the first challenge we give students, and we would present it just like this, in some sort of, we're using here Jiffy, a little app that we've used a lot for presentations with students and teachers. But we would say, okay, your first challenge in Scratch here is to draw a square. keeping in mind students don't have a lot of experience with Scratch, probably prior to this experience. So we'll talk about what's going on. Scratch is creating a square. After we've kind of got a good understanding of this little GIF, we're going to move forward, and we always talk giving this lesson kind of a low floor, high ceiling. So as we advance here, this is probably what I would have on my board as students were completing this challenge. So here are the blocks that you're going to need to be successful with this task in creating a square. We've got 7 of them. Few different ways we could go about this, but you're going to need these blocks on your screen. So we'd give students probably about 5 minutes. They'd drag these blocks onto their screen. And from there, they'd kind of work with the order of these steps until they get that challenge completed. And Mike and I have done this in small groups with kids. We've had them do it individually to start. Many different things, but it is super important in this process as they're learning, as always, not just jumping to the answer, giving them some time to think. So
I've also, not to cut you off, Ashley, I've started to do this a lot, and this is my first year. I'm also teaching computer science, AP Computer Science Principles, and I've done this a lot with that class as well. And a lot of times we call it like exploded code. I don't know where I got that from. I can't remember, but it works great. And then they can actually just play around with like thinking through a more limited selection of blocks. So it helps a lot to narrow down the selection of commands.
Yeah. So as we advance, and we're doing exactly what we told you not to do with students, we're giving you the answer here, just for our sake of time. But we would talk through there's a variety of ways to get to this answer. But I would say as we've run this lesson multiple years now, this is probably the most common response we see. So we would start here just talking through, again, kind of getting every student on board, that as we write code, we read code from top to bottom, and our Scratchy Cat is performing these operations, these blocks in this order. So if we kind of break down this code that we see here, it looks a little bit long. We start by putting the pen down so that our Scratchy Cat will start drawing. We're going to move forward 30 steps, turn at that 90-degree angle for our square, and we're going to repeat this 4 times, indicating those 4 sides. So as we go from here, another learning piece, we would then move into talking about the idea of making code efficient. So as we looked at that code on the last screen, the question is, could we do this same task with fewer blocks? And as we talk about, as Mike led with us in different, like creating apps and so forth, efficiency is really important as we look from the outside in and trying to make sense of some of this code. So as we look in Scratch, this is typically found in the control block, which are yellow. So
I'm sorry, did you want me to stay there for a second?
Perfect, that's perfect. So this would be our next task. Again, we'd throw this up on the board. Here's the code we just started with. I want you to do the same challenge. So draw a square, but using 6 blocks or less. And again, giving this kind of low floor piece, kind of sharing this repeat block is going to be needed to use somewhere here. So here's where we go again, revealing that answer. Okay, so taking that big middle section where we had move, turn 4 times and repeating this 4 times. So I'm seeing a good question here in the chat about, does clockwise or counterclockwise matter? Definitely have that conversation. I mean, as we talk about creating a square, we could really go both ways. In most shapes we could. I tend to lean towards that clockwise sense, but definitely could go both ways. So just
so you go back to this visual. If you turn the other direction, you just build the square upward, or the cat would build the square upward. So yeah, we don't really stress it a ton, but as we model it, we've typically done it like this. And another question that comes up a lot is like, what is this 30? That's pixels. So length of 30 pixels on each side.
Great. Yeah, so from here, again, kind of having the conversation of this code does the same thing, but this code is more efficient. This is kind of our goal. So we have students come to us all the time excited about some program they created because they have over 300 blocks in their program. And, it's great. We want to be excited for them. But again, that end goal is, how efficient is your program? So moving to task 3. Again, this progression is meant to kind of invite people in, but again, get a little bit more challenging as we move forth. And you'll see that as we move slides here, all while introducing pieces to Scratch to students with a math lens. So the second piece we would introduce is Scratch has this idea of, we call it sensing. These are these light blue blocks. So this allows people or users to type something in, and Scratch can do something with their answer. We also, in this next progression, are going to talk about data. So another kind of math sense as we compare coding and math, talking all about variables. Coding's very heavy, computer science very heavy with variables, and we're going to make use out of this for sure in this intro program. So I just want to kind of give a quick just kind of example of what this ask block looks like. So if you look here, it asks, what's your name? I type in Ashley, and it's stored actually in that little blue block. That's going to help us as we kind of read and interpret some of these answers that we get today. So everything that's typed in, stored in the answer. All right, so next challenge. What are we at? Challenge number 3. Challenge number 3. Can the user select the size of the square? So again, we'd keep this video up for a second, asking some of those questions like, what are you noticing? What are you wondering? As they're typing in here, so they're getting the option to input. When I type in 50, I get a pretty small square. When I type in 200, I have a much bigger square here. So as Mike stated, these numbers are really kind of pixel sizes as we talk about Scratch. So next challenge, we want them to be able to type in the size of their square, and their program should adapt to what they type in. So a few hints I would throw on the board for this challenge would
be that right there.
Yeah, great. Would be the sensing and the data pieces. So with sensing, the question we might want to ask users is, what is the length of the square? And again, that answer that they type in will be stored in that little blue answer block. And we're going to store this in a variable using data. So it's going to be under our data tab. Great, so let's see. And as I said, this is going to get a little more challenging as we move forward, so stick with us. As we go top to bottom here, the first thing that's happening is we're asking, what is the length of your square? Whatever they're typing in, whether it was 50, 200, we're going to store to this variable that we are naming side length. So we're going to call that number that they type in the side length. Now, everything we're doing from this point on is similar to what we were doing before. So we're repeating this 4 times because we're creating a square. But now, instead of moving however many pixels we had previously, we're going to move the length that they type in. So if they typed in 50, we're going to move that amount of pixels. 200, we're going to move that amount of pixels. So again, that variable is working a couple times within our code. Good. We're getting close here to the end of kind of our Scratch intro. So next,
let me just backstep. Did you have in here, Ashley, the progression from like square to triangle to pentagon and whatnot?
Yeah, that'll come.
That's what I thought.
Yep. All right, so a quick one more kind of new block here in Scratch, and then we'll kind of get to our, we would say kind of where we tear the roof off of, where students can go many different ways with this task. So our last piece here is going to be on randomness, and this is going to come in operators. So students tend to love this kind of this idea, this random piece, as they're creating games in Scratch. We'll find a lot of randomness is used for those games. So we'll present one more kind of task here before we get into kind of the heart of our lesson. So our hint here, we want students to create a square of random size. So every time I run my program, my square should look to be a different size. So again, we're going to have our variable, and we're going to need this block that allows them to pick random side lengths. So we do want to kind of give ourselves a range here. 10 would give us a very small square, where 200, we don't want to get much bigger than that because it would exceed the size of our screen. Leading us here, just one more kind of different spin. And again, as we do these challenges, our goal is to get students familiar with Scratch while using some of these math skills. So this first one we'll see, it's going to set our variable that we called side length to one of these random numbers. Every time we run this, that number should be random. And then we're going to do the same task below. Based upon what that side length comes out, that random number, we're going to move that far and create our square. So previously to this screen here, the challenges that we created were really just addressing in a lot of our presentations, people saying, well, how do you present this to students in a way where you can really you can share that you're doing this in the math classroom. It's worth your math classroom time. So that was kind of our low floor piece, get people introduced so that we could really hit kind of this bigger task here. So a couple challenges we would pose. We would say, first off, and this is where Dan Anderson, as we presented, this is kind of where his presentation started for us. So we asked students to draw a triangle, and again, giving them another task for students that might conquer that quickly, a pentagon. And we could continue, we could go up to hexagon and so forth, but here's where we'll start. So similar format, giving them the blocks that they'll need for this challenge. We love this challenge because this is what students see as they're creating their triangle. Any thoughts as they are using their code here to create their triangle? What might be going on? And we love this. We love for some broken code. Creates really good conversations. As I look at the cat moving here, it's moving forward. I think in here we've got 30 pixels, and then it's turning 60 degrees, doing it again, turning 60 degrees again. Go ahead and flip one forward, Mike.
Mm-hmm.
So this is a fabulous conversation to have with students at this point. Again, a lot of math terms. So we get to keep that math at the center of our focus here for our lesson. Oh, yes. Great. We got somebody who guessed it here. Okay, so as we talk triangle, as we're moving those angles, we were just working with 90 degrees in our square. We've got students, of course, and even teachers, as I did this lesson for the first time, we're turning 60 degrees, the angle of the triangle. And great conversation to have. And again, when something goes wrong, that's a really nice piece. We talk about sometimes when tech can pair with us, it's great to see at an instant that our code is not working. So as we move in, and I'm seeing a lot of great comments here, we need to be using the exterior angle rather than that interior angle. As we talk about Scratch turning, in this case, clockwise, we're turning the exterior angle amount. So again, great conversation around interior and exterior angles. And as we're creating this shape, which angle we should be using. So, I mean, we get to kind of feel out how our students are doing at this point. Might be a day, might be a couple days for this progression, but our big goal and our goal with code is we want to be able to generalize something. So this is great. We created a square, we created a triangle, we created a hexagon. We should be able to start to now notice patterns so that students can run this program for any regular polygon. And that's our goal with our program. So we'll show you again quickly here how we might go kind of full swing with this lesson. So the first thing we'll do is we'll create a variable, and we'll call this the number of sides. We're going to ask here from the start. Go ahead and flip here, Mike.
Yeah.
Thanks. So how many sides does your shape have? So we're going to ask. So the person using our program will be able to type in how many sides they want our shape to have. And we'll store that in the number of sides here. So we'll see that piece coming. Now we'll also see we're going to repeat this based upon the number of sides. So if we're wanting to draw a square, we'll put this in 4 as our number of sides, and that's how often this will repeat. Okay, next from here, again, we apologize, we're going through this a little quickly, but we'll get kind of the gist of it. From here, we're going to move however many steps we want. Again, that step, I put 80 in here for my example, just shows how big our shape is going to be. It's the pixels. But then we get to have this conversation, and this would be a fabulous kind of trial and error to see how we can talk about what angle are we turning. And you guys nailed it in this chat here, that we are moving the exterior angle amount, not the interior angle amount. So you'll see as we turn here, exterior angle kind of formula piece is going to be 360 divided by how many sides we have. So this code here, as we've created this program, and students feel really proud of this as well, giving them, a few minutes to try this for a bunch of different shapes to show that the program they just created can really work for anything here.
And so, yeah, this now becomes, I guess we didn't put in a slideshow of what this creates, but as soon as you input, like let's say you inputted 7 sides, it would turn the variable angle based off of the formula.
Great. Yeah, so let's pause here. Let's just open it up to the chat for a second. As we look at, again, we kind of call this a great intro lesson. But you can see that this lesson can go many different directions depending on the students, maybe the age you're working with. But what math standards? I mean, that was our focus. We said any coding lesson we're doing, we're math teachers. To justify using this in our classroom, we really want to keep that math focus. Oh, I love it. In addition, the cat could be saying angles as it's making turns. So talking about some angle measures is great. We talked just earlier in the chat here, interior and exterior angles. Number of sides for shapes, naming shapes. Lots of really nice stuff, you guys. Thanks for tuning in.
And so obviously it's pretty flexible. I think, as we've presented this numerous times, we like it because of the low floor, high ceiling nature of it. But you can make, if you actually, at the end, we'll probably show you where you can find this lesson on our website, but there's challenges that take the ceiling off of it, making different types of shapes. You could make it so it makes one shape after the other and so on. So definitely could hit elementary standards in terms of geometry shapes. It could even, with the formula and exterior focus, you hit a lot of 10th grade standards for geometry. So great one. We ran it this year in geometry. It was definitely well received across the board, and kids really just get into it. The next one we're going to talk about uses a different platform, and I'm actually going to break out for part of this and show you that platform called Beetleblocks. And we decided to call this lesson Solids of Extrusion. Again, there's a link, there's a link down here at the bottom of a video we created for it, and a QR code if you wanted to go there. It's just going to be a little more in depth than what we could definitely cover in the webinar here, but we'll give you the links to this at the end too if it's too fast for you to write down. So if I just step out and leave here for a second, if I go to beetleblocks.com, I guess I could back out to just that. So for Beetleblocks, if you wanted to go there, you certainly could. It might be easier for tonight just to watch, again, just because of time. But I can just run this. You definitely want to create an account. But again, we could do something similar. Notice the window here is very similar, but instead of Scratch the cat, you got a beetle here. And that beetle is just going to move around this stage out here. So if I did some exploded type code here, I could say pull out some starter events, like when the flag is clicked, just like Scratch. I think this program is based on Snap. It was built off of Snap. A lot of times, like we did with the other one, they liked some kind of reset button. So when the space is pressed, that event to do a complete clean and reset of the beetle. And then I'm going to put some code out there. So if I put out like a move block, pull out a rotate block. There's in the control menu, there's also repeat blocks. If you pull those out, and I suppose like the pen tool where you put the pen down, this environment now has a 3D pen, basically like a 3D printer where you can start extruding. So if I put this to extruding, the lines work a lot better for things that are boxy like we're going to do here. If I did this code, could you frame it to make a square? And I'll just pause for like 30 seconds so you can think about it. Maybe even blow the code up just a little bit. So hopefully you're thinking, yes, similarly to before, you'd want to put the pen down, only this block now acts like the pen. You want to, in making a square, you'd want to move and rotate. And let's say we wanted to make a square that was like dimension of 4. I could just make a 4, again, turn 90. I could talk a lot about these rotations, like which one's X, Y, and Z. I'm going to hold off on that just because it can get pretty tricky, but it's definitely explained in the lessons we have. And instead of repeating 10 times, repeat 4 times. So then, again, we didn't model the Scratch, but if you model this, it's very similar. You got a green flag, and notice that it would draw a square. So if I jump back to our if I jump back to our slides, I would definitely give kids the exploded code to start, something like that, and then we jump back and say, okay, well, what if we wanted to fill that in like a base of a solid? So we really like this lesson from when we started into our lessons on solids, even previous to surface area. Not just waiting to like volume, but talking about area. As soon as you get done with area, then branching into surface area. So in computer science, we call this code has been abstracted because you don't know what's behind this function called square base. So that is kind of disguising some of the code that makes it. But you might be able to do the same thing again where you think about like what in the world, there's multiple ways that obviously you could fill this in. Like you could do more of a zigzagging approach, but if you see the one on here, how would you do something like that? And yeah, I'm guessing you can also post ideas to the chat too, but I'll kind of just pop back and forth here. You probably noticed this block that says set length to 4. So we're doing just like we did in Scratch. We're making a variable, and we're saying, let's make a variable, and we'll call it length. Do apologize if that's pretty small, but you can probably see it pretty large over here. And then it will show up, let the actual length will show up over here in the field. So if I do originally here set the length to 4, now instead of moving 4, I can move length. Now just like we did before in Scratch, this gives us a little bit of room to play around with the length, make the length variable so it can change easy, right? And again, bringing in this concept of variable and how it's helpful in the programming. And hopefully you thought, well, it's just repeating squares. They're just getting smaller and smaller and smaller. So what we're going to do is make it smaller. I'm going to pull out this change block. So we've made 1 square. Well, then let's decrease the length by a little bit. Instead of decreasing it by changing it by 1, I'm going to decrease it by making it negative. I'm actually going to go pretty small so there's an overlap. That works a little bit better when you print it so there's not gaps in the print. So that says -0.2 if you can't read it. And so we'll decrease the size, and then we just want to like loop back through and make a bunch more squares. So I'm going to pull out the control block. We thought at some point here it could be good just to show you the writing of some code in case the GIFs left you short. So let's say I repeated this 10 times. Let's just run that and see what happens. It doesn't quite fill out the base, but notice that it made 10 of them, slowly making them smaller. 0.2 smaller 10 times. I guess that 0.2 times 10 is 2, right? So now we have half that length of 2, if you can see it over here. So to make it decrease to 0, there's also, you can repeat until a condition is met, like until length equals 0. But just to make things a little faster here, and for today, I'll just make that 20 so that it builds it all the way down to 0. Notice also when I press the spacebar, remember we made this reset, and so you can reset when you press the spacebar. So I'll run that, and now it makes the full base. And what's interesting is what we can do is, since this makes a base, what we talk about so much in algebra is like functions and what they do. Sometimes the functions will take in like parameters, like an input. In this particular case, we don't need it to. We could make it so it does, like make it take in length for a parameter. But I'm just going to show you here like a basic concept of what I was showing there to make a base. So I'll title this base. To make that base, I can just do this code. This code made a base. And that's a little different than the way that Scratch does it, but we can define it, and now all that code is in this one block. So if I pull this single block out, I guess I called it square base. I should have kept it consistent with what was on my slides before. But I'll reset, and notice if I run that, it makes that square base. Not too much to rename it. I can just right-click it. You can always do right-click to make edits, which is a good thing to look at. And so I'm actually going to change that to square base. Okay, so now that we got a base made, again, we're just trying to layer it up and talk about what's happening in a solid, right? So in a solid, you have a base, and then extruding up off of that base is like the walls, or what we often call like the lateral area, the lateral sides. And so how could you build that up knowing what you know, just the basics of what you already know? You might also notice we changed the color, and I like playing around the colors. Kids like that for some reason. They like just making it their own. So there's a hue button in there that you can actually change the color. But a lot of you are probably saying, well, you just keep making squares and you just keep building them up, right, in the Z direction, because there's a third dimension now. So there is a block for that. It's called motion change absolute. In this case, we're going in the Z direction. So you're changing the absolute Z value by, again, I'm going to go something small because then it kind of meshes the squares together. Like change the absolute by 0.2. And we don't want to make a bunch of squares over and over. We just want to make one square. I guess I could have saved some of that code, huh? So if I could have actually abstracted it out twice where I made another function called square. Let me just go, well, I got time to just make a new one. So if I just go to repeat, move length, which we do need to reset that to 4, because remember the length now is at 0 since it wound it all the way down. So before I do that, I'm going to set my length back to, sorry, I keep running this code, set my length back to 4 at the beginning. And again, notice how we're already getting some errors because I didn't have that in there. That's why we found the block base is really the best, because if you start doing text-based, which we definitely tried a lot, the errors really can be overwhelming for the kids to start off with. You can eventually bridge in, and we like Python for that, which we can possibly show. Let's see here. So if I go and just finish this off, if I turn, rotate the Z again by 90, which is how we made our original square, then you can see that I could, again, loop that a number of times. So this is going to, if I just run it once, notice that it will notch up and make one square. So see how there's like that little indent where it made another square. I could just repeat this a handful of times. So I could do repeat, and I'll try to structure it so it loops this in. Each time it wants to change the absolute Z and notch it up. So then I could run that. And notice how it does that. Again, each time you're probably going to want to reset it. And just to make it a little taller, we'll go up to 20. So hopefully seeing the live code helps a little bit. We wanted to show some live code, and hopefully it's helping you just to kind of see what in the world is going on. So make a block, and I'm just going to make this one, and I'll call it like the walls. And I will take this code in here that makes the walls and abstract that out just a little bit. And if you're wondering how to close that top off, like if I was to run this right now, notice how it's going to leave the top off. Can you think about what you would put here to make another base? You know, hopefully you were thinking maybe just make another square base, right? Because it's congruent and parallel to the bottom, which is what kids say as well. So just the one last run here. Notice that it makes the walls and then closes off the base. Sometimes kids likes to actually look inside this thing and float around and play around. But really, the sky's the limit here with this. I just wanted to show you one basic program that we could execute. So as you're doing this, you can think to yourself like, don't forget to emphasize what you always emphasize. Like, look, the lateral faces are what wrap around. If you're really going to end up building up formulas for surface area, make sure you can even put in non-examples. Say, hey, could you make one where the bases weren't parallel? You know, you can mess with them and giving them challenges depending on how they're doing and how much time you have. Stress the importance and the value of making that side length variable. And then I just wanted, again, to give you a glimpse at some functions within there. So hopefully, depending on your background, that was new and it was interesting. And there is so much you can do here. When we did this, we ran this at an NCTM 2017, I think, 2017, I believe. Jess Brewer's, our math coach, was there and was kind of following along. And by the end of it, she was already, and she had never written a program before. So shout out to Jess. She had this going, this Ngon maker, and it had inputs that it was taking in because we had done the Playful Polygons before that. And we've done this with our kids as well without any direction, because if they've done the Scratch beforehand, they've got the concepts of how to make different polygons down already. And then again, the really cool thing, depending on what you have access to, and this thing will start over from the beginning here in a second, but if you have a 3D printer, you can 3D print these. And we had kids making nets off of these. And then instead of giving them new formulas for surface area, you could spend time deriving them. And they really like having their own blocks in their hands while they're trying to trace out the net and think about those areas. So it's very interesting. If you have digital calipers, you could actually measure things. So they're getting hands-on, like some hands-on measuring, and then actually calculating some surface areas or volumes. So a lot of potential to branch out.
Mike, I'm seeing a great chat here from Jim.
Yeah. No, pause and address it.
Yeah, she came to an idea about students creating housing plans and then like a 3D model, which I think is an awesome connection to what you're seeing here as you're talking about nets.
Say that again.
Yeah, Jamie had this idea here. She asked, have you had students code housing plans or a 3D model of a house? I think that'd be great as you're looking at these nets.
Yeah, that is a great idea. So I know we've done something where a few years ago we made designs, but I never thought to code it. That's a great idea.
Yeah.
Sweet. We got a new extension.
One other piece I'm seeing here a lot in the comments, and is kind of a frequent question we get. So again, we've kind of said our goals as we use this code in our classroom is we have a big center on making the math visual. And so we get a lot of questions about, you know, like I'm seeing in here, have you used processing, or have you used Python? Have you used these different platforms? And we find really just finding a platform that works for you and your students is the most important. You can already see some of the parallels between, as we even talk about two different platforms here, Scratch to Beetleblocks. You can see really the ideas, the logic behind some of this code, rather than maybe getting familiar with all the different platforms. But a question I see in here is, are we going to be expanding? Right now we're very Scratch heavy, but we do have some plans in the coming year to start expanding to a few more platforms.
Yeah, and definitely. And we've actually done a lot of this. So I don't know if you guys caught when Ashley was saying at the beginning, like, so when we were like, oh, what do we want to do with making this coding geometry class? Do we want everything to be coded? And what we ultimately decided was not really, no. We don't want to ditch a lot of the classical pieces. We just want balance. We want balance and exposure. And Python is my favorite, and I love it. And I've tried to do it with kids. They don't navigate to it quickly. You know what I mean? It does need a lot more time and detail if you're going to try to go text-based to start. So we found it to be, if you want to do one thing per unit, start with Scratch, and then maybe somewhere towards the middle of the year you can bridge it in. We do have a bunch of Python lessons. There's even some JavaScript ones that I've pushed around with, but again, we don't get the same experience as a whole with our kids in core math classes we're talking about now.
Mike, you want to jump to your code-necting the dots lesson?
Yep. So just to flash through these, if you're a calculus teacher, you know, you could make solids of revolution. That's not that hard to do. So just by changing, instead of moving, you can do rotation. And so there is a lesson online called Solids of Revolution, but I can kind of skip over some of this. This is one a student did, just so you can see something that was curved. So yeah, and then we started going a little bit more coordinate heavy here as of recent, and talking about like how could we get this down to like some of the elementary level standards as well. And we used to always just graph. I don't know if you see on the right, we used to always graph like Batman. We do different symbols, and kids would try to get some points on all the coordinate and all the quadrants. We try to get some points on the axes. We do the similar thing here, and so we wrote this lesson for kids really struggling or just learning coordinates. And it works great because when you're writing the code, what they get is like live feedback. Are their points connecting correctly? Because typically what it is, you get a list of points, and then you write those points down, and then you have having erasing. Not that this isn't good, it's just as good. But this is a strong lesson. And what it ends up doing is it allows you then to branch into something much harder. So notice here it's very similar. You're going to erase everything, put the pen up, set a pen size, and now you're just going to do like a connect the dot. Go from here, put the pen down, go to there, and you could just string points and essentially make a connect the dot. So that's more for like upper elementary, even middle school, sometimes really good. Jot this down if you've never watched this TED Talk. I've probably watched this at least 15, 20 times. And I watch it every year with the kids. It's called The Math Behind the Movies. Tony DeRose from Pixar talks through basically the animation behind their movies and how they get their characters to move. So jot that down. I don't have it linked here, but you just Google that title and you'll find the TED Talk. And we then put his ideas into practice this year. And so now all those points we did in code-necting the dot, we're able to pass those through functions. Now the pink block you see here is a lot like the blue one we showed you in Beetleblocks. And what you're going to do is pass those points through a function. And it will affect every point that you pass through it. So by doing this, we can get have the kids graph their own character. Like I graphed a fish. I had kids graph like a tiger. I was going to put some of that on here. I just figured it'd be too much. But first year we ran it, they were able to make it translate. They were able to make things dilate, and the mathematics behind those is explained in the movie. And then I challenged them to make it rotate. This was an extension because it uses trigonometry. So we hadn't gotten to trigonometry. I essentially just had to show them the formula. But this would also be a good one for if you're teaching trig identities in some of the upper math levels. You can get that to be very visual. And we found those to be great lessons.
Yeah, so we're looking at, we got about maybe 5 to 10-ish minutes here at the end. We just wanted to whip through a couple last minutes here, but our goal kind of as this presentation tonight was just to get you thinking about how you could connect code into your math classroom. And I see that we've got a variety of age groups that we teach and subjects, so forth. So to kind of close us here and get you thinking a little bit, we gave you our lesson, csandmath.org. I want to kind of brainstorm through here a couple lessons you might find on our website. So we'll just highlight a couple and get you kind of thinking. But again, if you see something that interests you as you look at our website, Mike and I are always creating new lessons. So just give us a shout out here at our email, and we'd be happy to create something for you.
Do you want me to go out to the site, Ashley? What you thinking here?
Let's go ahead and just kind of flip through some of these lessons here at the end.
Okay.
Kind of
some of these here?
Yeah. Sure. So just because I see we got a variety, we've got elementary, kind of middle, and high school as we section through a couple of these. Here's a great one. We said this was geometry focused, but let's kind of open up to some other potentials here. This one talking about the calculation of tip. So we're working with percentages here. As you see, this program, students get very into the visuals as well. Their bill was $43. They're wanting to tip 20% and coming out with the total bill. Just getting you thinking a little bit. Jumping on to our next one here, similar to some payments. As you look at this, this would be kind of an elementary lesson again. If our bill was $30.16, students can actually click on the screen as they select what they want to use to pay this bill. So the student chose to use, you'll see on the left-hand side in this table, a $20 bill, $10 bill. We've got some change here at the end as well.
And they're actually building this. They're not just using it, right? They're coding this up. So
exactly. Another elementary, one more elementary, then we'll move to middle. Area of some of these shapes here. So as you click any of these shapes, as we click this triangle, it asks for the base and the height, and then shares the area. So again, they're not just using this, they're coding this. So having the math behind these. And all of these lessons available on our website. As we move forward to some middle school lessons, we've got positive exponent calculator. So calculating exponents, we're working heavy in that right now in my 8th grade algebra class. So talking about the math between, we've got some loops here as we calculate 2 times 2 times 2. Another middle school lesson, some probability. Really, really nice with probability and coding and creating some of these simulations or these trials. You can quickly run a coin flip of 1,000 coin flips in a matter of seconds, rather than maybe the crazy chaotic classroom for a period of coin flips, which is great too. But we can simulate things, which is great. A high school lesson here, we got quadratic formula. This program, as students coded this, solves for the zeros of our parabola. In this lesson here, we're putting $1,000 in. We've got a percent return of 20%. And we're looking at what the future value of this money would look like after a certain number of years. So Mike, you ran like a, what was this called again?
Yeah, so we were we did a financial literacy type of unit, and then this particular one, they were trying to figure out, okay, if they invested in certain types of either you can do stocks, bonds, you can talk about different mutual funds, and just talking about the potential of what your money could look like, and if you're able to pick a good investment, how much money you could make over the long run.
Yeah. And to throw here to finish for today, another kind of notice wonder or which one doesn't belong here. You could zoom in on these pieces, but again, this is some code in Scratch and some probability. If we look at that top left, we're looking at running a heads and tails trial. So it's a coin flip. We go over to the right-hand side, we've got a rock, paper, scissors trial going on. Bottom right, talking about the probability of an even or odd number.
Yeah, number cube.
Yeah, and bottom left, this was one Mike ran in his classroom that was fun, but calculating the 3-point percentage of Steph Curry here in this last one. So whether he's going to swish the basket or miss it.
And so this kind of brings in, if you saw Christopher Danielson's Which One Doesn't Belong, it's often an acronym, WODB, so which one doesn't belong. This is kind of, we've extended and branched it into code, and the kids really thought it was interesting and then tried to pick out which one doesn't fit and why, and they had to reason through the outcomes and if it's programmed correctly and everything like that.
Yeah, so I am throwing in the bit.ly here to our chat for our presentation, so you can find all the links and resources in here. Mike, with our last couple of minutes, you want to wander over to our website just to kind of show some of the different pieces we've got on here?
Yep. So we have, like I said, all the lessons are free. We're wanting people to use them and give feedback. So let's just say we went to high school lessons. You'd see things that we haven't done, Mandelbrot, some fractals. We have more, maybe some taxes. We have programming any formula, like conversion formulas, and how to go about those. And Ashley organized these by strands. So you got algebra, guessing functions, exponential growth. Stacking cups is a classic for linear, multiplied binomials. And we've tried to start to branch these out a little bit, so we got a little bit more modeling, but we're very focused just on hitting targets at the beginning. So we got grasping gravity, like what would a ball drop look and why would it fit quadratic?
So some modeling.
Say it again.
Just some modeling, which is great.
Yeah, right, exactly.
Any of these GIFs that you see on the website, they're going to open you, as we kind of started, with a student guide and a teacher guide to really support you in running this in your classroom. But
so if I just clicked on Playful Polygons to end, if I just click that just to show them what they would get. So then it just has, you click the lesson downloads, you go there, it's got the teacher guide, it's got all the directions, it's got a student handout, it's all free. So this is what the kids would actually open and work through. Notice it has the kind of progression we already talked through. It has directions. One kid typically has this open and the other kid has Scratch open. Works well to partner them. Again, here's the kind of the extensions we had mentioned that we didn't have time for today, but you get the idea here.
Yeah, so again, with anything new, whether you've taught code in your classroom before or not, really, it's a little scary to try it at first, but we found, as Mike shared at the start with these kind of reflections from kids, it's great to kind of approach math in this maybe different way than they're traditionally seeing day to day. And students really do grasp onto some of these ideas. And we like to believe the concepts that they're learning are solidified a little bit deeper as we engage in some of these problem solving activities together in these programs. Well, thank you guys so much. It looks like it's about our time. We got a minute to end. Mike and I will stay on for a couple minutes here if you want to throw some questions in the chat. Otherwise, we've got our email and Twitter handles in the presentation I linked in here. Thank you.
Hey, for those that were wanting Python, I can throw a quick recommendation out. There's a guy named Peter Farrell. He does. He's written several of these books. We've coded a lot from him. Math Adventures in Python. If you wanted to have some Python lessons, I highly recommend his work. Again, that's Peter Farrell. If you wanted to look up his work, he's got this one, Math Adventures in Python, and another one with Python as well. If you wanted specific Python lessons, his are really strong.
Mike, will you throw the link into your TED Talk into the chat?
Oh, absolutely, yeah.
All right. Well, thank you so much.
Yeah, thank you. Thanks.
All right, everybody. So thank you for attending this evening. We did hit our, 1 hour in here. So thank you for spending your time with us this evening. Next week, we do have our Global Math Department again, and it's all about using Desmo's snapshots to help deepen equitable classroom discourse. And our description of the session says this workshop will explore how to integrate Desmo's snapshots tool with any curriculum to deepen discourse, differentiation, and formative assessment. We'll examine how to amplify every student's voice in a classroom to create more equitable participation. The 5 practices for productive mathematical discussion include anticipating, monitoring, selecting, sequencing, and connecting. Using Desmo's snapshots tool, you can develop a more robust understanding of how to infuse these 5 practices into any lesson. So we look forward to seeing you back here at the same time, same place next week for that discussion. And remember, this recording will be available typically about in 24 hours for you to review and share with others. Thank you so much, everybody.